It is the top of the hour, and we have had a lot of comedy here leading up to this moment, but I'm ready to get us started here with the Telos Alliance Container University. And I'm Lindsay Klinger, the Digital Marketing Event Manager for Telos. This is the second webinar in a 5-session series for Container University. So we're really excited to dive deeper into each one of these learning sessions, so stay tuned for more. Let me introduce you to a few other folks that I have on the call today. We have Kirk Harnack, the Senior Solutions Consultant. He is guiding us through today's webinar. This is a learning session, so we welcome all of your questions. So please feel free to use the toolbar at the bottom of your screen and submit those questions at any time, and we will happily answer those for you. Angie Robertson, our marketing director, is leading all of those Q&As, so she will work with the team and get back to you as soon as possible. And the panel of experts that she's leading here is Cam Eicher, our Senior VP of Worldwide Sales, Marty Sachs, our Executive Vice President of Sales, Support, and Marketing. We have Greg Shea, our Chief Technical Officer, and Jake Alderman, our Program Manager of Virtual Solutions. And like I said, together, they are working diligently in the background to answer all of your questions. Lastly, before Kirk takes us away, is to not forget that by attending this webinar, you can receive a half credit towards your SBE recertification efforts. So with that, Kirk, take us away.
Thank you very much, Lindsay. And do remember that you can ask questions by hitting the Q&A button there. Well, software containers are becoming the industry standard for performing microservices in efficient and reliable ways. And this technology is already widely adopted in the online services industries, including financial payments processing and thousands of other critical applications. In this session, Container University 202, we're discussing the audio technologies that connect the different building blocks in our new broadcast infrastructure. And some of this infrastructure may be in remote data centers or in public cloud computing facilities. You may have your container infrastructure totally on-premise, though, so we'll be covering that as well. In this presentation, we're going to examine different audio over IP, or AoIP, transmission formats, such as Unicast and Multicast. We're going to determine when an IP transmission codec is appropriate for connecting audio between or among virtual or physical broadcast infrastructure systems. We're also going to try to understand the technical considerations and constraints leading to ideal deployments using the correct technologies. And we'll consider how both economic and technical constraints factor into AoIP format selections. Now, as in our first two Container University webinars, Greg Shea and Jake Alderman are going to join me with critical information and answers to questions surrounding our specific topics. Greg is our Chief Technology Officer, as Lindsay said, at the Telos Alliance. Mr. Shea co-developed audio over IP for broadcast with both the LiveWire AoIP standard and the global AES 67 standard. Greg holds a patent on the critical clocking techniques that make low latency audio over IP work. Jake Alderman is our Virtual Solutions Program Manager. His work involves making the technology we're about to describe actually accessible to broadcast engineers and broadcasters as well as to IT technicians. Okay, I got to show you this slide just to kind of bring us all together where we are. This is how we got to software containerization, starting with the pre-virtualization scenario on the left. This is when we simply ran applications on an operating system. Now, we still do that today, certainly on our desktops, laptops, mobile devices. Probably your computer automation system still runs this way. In the early 2000s, multi-core CPUs made it possible to load up a physical computer with more work. And thus, the hypervisor was born, allowing multiple operating systems to run on the same powerful hardware, getting more use out of it. Each guest operating system could be Windows or Linux or perhaps something else exotic. Each OS required the usual amount of care and feeding and patching and upgrading as we normally associate with complete operating systems. So as such, each guest OS in a virtual machine tends to carry its own level of baggage along with it. Containerized software was developed with the notion that a more lightweight environment would work just fine for each application. Only one underlying operating system is needed. Typically, this will be a Linux-based server environment. The container engine gives each container the attention and the resources that it needs to do its designed job. So here are some examples of some of the broadcast functions available right now to deploy in software containers running on server platforms. Full function audio mixers, broadcast phone systems for talk shows, news gathering, and contesting, as well as broadcast intercom systems. And these are really the systems, these are just the systems from Telos Alliance at this time. More broadcast functionality is roadmapped, and features are being added as well to these existing ones. Moreover, other broadcast equipment manufacturers are committing now to containerized software infrastructure. All of these containerized broadcast systems run on server compute platforms, and they do that whether they're on your premises or in data centers. So as with virtual machines on a server platform, different software containers can be installed on a single server, and that gives us multiple broadcast-related functions. So in this graphical example, a Linux operating system is installed on the bare metal computer hardware. Now within Linux, we'll install a container runtime engine like the Docker engine. And this Docker engine will then service and support the broadcast applications that we install in containers. These applications are typically going to be containerized audio consoles and phone systems, intercom, other functions such as audio processing, profanity delay, and more are going to become possible as well. Containerized software can interact with other software containers using an audio over IP system. This AoIP can be over an IP network that's actually internal to the server's host operating system. Now, this virtual AoIP network within the server can then connect to a physical AoIP network outside the server. And this allows external hardware like Telos vSet talk show controllers, intercom panels, X nodes, and other hands-on broadcast gear to interact with the containerized broadcast functions. So in this example, we see hardware, broadcast equipment, and containerized broadcast software both operating within the same physical plant. Except for that radio transmitter in the upper right corner, this broadcast gear is all in the same physical location. It's all on the same LAN. Now here we've simplified the diagram slightly, and we've added a remote talent working from home. The remote talent is connected over the public internet and has secure, encrypted remote access to the audio consoles at the studio. Remote control is performed using a regular web browser, and that same browser can provide two-way audio transport using the audio codec functionality that's available in today's web browsers. In this diagram, the remote user's audio is carried using a transport codec like AAC or Opus. The local IP audio at the studio, well, that's all multicast audio over IP, as you'd find with any other axial live wire network. So our topic at hand is sorting out when multicast, unicast, and codecs are the correct methods of moving IP audio from place to place. So let's start by introducing the multicast and unicast approaches. I'm Kirk Harnack along with Greg Shea and Jake Alderman. Gentlemen, multicast protocols are commonly used in audio over IP systems. In fact, if you've had any experience with Livewire or Axia, you've probably used multicast and only multicast IP audio. However, the unicast addressing mode is also employed in certain cases. I got to ask, why do we have to have these different addressing modes for different AoIP scenarios, different networking schemes, or different end goals? Why do we need to have multicast or unicast?
Okay, this is an interesting question, and there's a bit of history here. And the history is why we chose multicast, because multicast at the beginning of Livewire is a particularly good way to work together in a facility, and it gives you the property of having all of your signals available everywhere, always. And that's hugely important when you're doing a live show, and anything can happen at any moment. And you may need to run in the back room and monitor, is that microphone working right? Does this sound okay? So when you're running a live show in a facility, multicast is really handy. That property of having everything everywhere. But unfortunately, the internet does not carry multicast. And a lot of the design of servers, and for instance, in the cloud, is not planned to support multicast. So our favorite tool that we've been using for years isn't available. So we simply also support the other mode, Unicast. And Unicast simply means it's a point-to-point connection. Instead of the audio or the signal being available everywhere, you have to decide ahead of time. This is going from point A to point B, and that implies some pre-planning. That implies you can't jump in and listen to it at multiple places unless you send an additional copy of what's being sent over. So it's both has its advantages and disadvantages, but it's largely a historical answer.
When we look at how facilities are planned, as Greg said, we had our best friend Multicast for a number of years. And as we've evolved and had more interoperability also step forward, Unicast has come in as a key player. So whether it's the ability to connect to a third-party device in a facility, which occasionally we need to use a Unicast stream to meet that format, or beyond a facility, Unicast is certainly a tool in the toolbox we should all start becoming more comfortable with. So just because multicast is all reliable that we're used to having in our toolbox and the one we lean on because it works best for most use cases, doesn't mean that Unicast is in any way a bad protocol. Also, when we look at things from a networking and an IT perspective, multicast has always been a special use case tool. And special use case tools always take longer to be adopted in the IT industry. So Unicast is here today. It's not to say multicast won't be more available tomorrow, but we're here to tell you how to make things work in the short term, not the long term. So we're going to talk about how Unicast is a key player in complementing multicast to facilitate broadcast workflows.
Now, let's put some of our broadcast infrastructure into a cloud data center. This hosted broadcast functionality could be a backup system intended for, say, disaster recovery. Or it could be used for adding extra programming during, say, playoff season or election coverage or holiday music. Whenever extra broadcast production infrastructure is needed, it can simply be spun up quickly, well, say, in a data center, off-site if you like. Now, consider again the audio connectivity between and among these separate broadcast facilities. Most any on-premise audio over IP system is going to use the multicast distribution method. Greg Shea is going to explain what this means and what the benefits are in a couple of minutes. The general rule of thumb is that multicast is a convenient and very efficient way to distribute high bandwidth, low latency audio streams or channels on a local area network, a LAN. The public internet doesn't support multicast, so we can't use the internet for that, but on a LAN that's configured for it, multicast is an ideal routing and distribution scheme. When we move broadcast functionality into data centers, we don't always have access to using multicast protocols. However, using Unicast addressing usually works just fine. There may be an additional extra cost for using multicast in a data center or a cloud environment, but Unicast doesn't incur any extra data carriage expenses within that data center. Greg Shea and Jake Altman will have more on Unicast shortly as well. Now, when we want to transport audio over the public internet, it's commonplace to use some kind of audio transmission codec. Now, there are benefits to using a codec, and those include, of course, audio bit rate reduction, so we're sending less audio, less bytes, I should say, less data, along with some built-in error concealment and built-in error correction. Now, since data cloud centers usually charge for data ingress and egress, I mean, it's a very low amount, but it does add up, using a lower data rate for audio in and out of these data centers is worthwhile, especially for long-term operations. The key concept here is that there are different ways to transport IP audio, and each has a best use case, and that's what we're continuing to explore in this webinar. Some broadcast equipment, even when equipped with AoIP audio connectivity, still has legacy XLR or other hardware audio connections on it. I mean, the equipment that you buy and put in your facility. Software containers don't support legacy analog or AES-EBU connections, in part because, well, servers don't have XLR connectors. Also, servers may well be in a secure data center. Jake explains that AoIP is actually the absolutely perfect input-output connection for containerized software infrastructure.
When we think about a container and how it functions with a broader system, one of the easy things to remember when we talk about audio input and output is the only option is Livewire or AES-67 audio streams that go in and out. And when we start to think that way, it might sound a little daunting because we're losing our XLR connectors or Studio Hub adapters or RCA inputs that are on the back of physical hardware products. But this is no different than what we've been doing for a couple decades already with products like the Axia Studio Engine or the Telos iPort or the VX Enterprise platforms, which are software running on a compute platform where the only audio I/O in and out of them is Livewire or AES-67.
Let's look at some differences in a multicast flow versus several unicast stream flows. So multicast on the left side there is based on a system of advertise and subscribe, or maybe you'd call it publish and subscribe. It's really efficient in a qualified network, and bandwidth usage is minimized to the minimum it takes to get all the job done. Unicast, however, is based on a push to each receiver, and that is an individual push to each individual receiver. The bandwidth is the stream bandwidth times the number of endpoints you're sending to. Now, it is simple. Unicast is simple. There's no IGMP querier needed in the switches, and there's no multicast qualifications for the switches. Notice that in multicast, that the originating device on the left needs to send only one stream. The receiving devices simply request a copy of any stream they want, and it's the Ethernet switches that forward the requested stream. It's not the originating device. It's the switches that do this work. The multicast qualified Ethernet switches are doing the hard work of answering requests to join or to leave a stream and carrying out that request. In a unicast model, the sending device has to send one copy of the desired stream to each device that wants to receive it. And it's not as efficient, but it is simple. And the switches or other network devices need to be qualified to work with multicast streams. Anyone who has installed or maintained an AoIP media system probably knows that multicast is in use. Indeed, these systems depend on that multicast IP functionality, both for convenience and potentially for bandwidth capacity concerns. Greg Shea here asks and answers a key question for understanding the role of multicast in IP media networks.
What's multicast very useful for? As we've mentioned, it has this property of all of your signals in your plant are available at any other point. So not only you don't have to pre-plan where you want the audio to come out, but you can on the fly make decisions. You can on the fly be back working as an engineer in the rack room and monitor and plug in and listen. And there's an important property here is that you are not disturbing or changing the configuration of the source. So you're not in any way taking any risk of anything having to do with your on-air program. You're simply listening to it. It's very much like the old telephone butt set where you're, clipping on and basically listening in to the audio program that's already there.
IP multicast is a technique for one-to-many real-time communications over an IP infrastructure in a network, and it scales to a larger receiver population by requiring neither, again, prior knowledge of a receiver's identity, nor prior knowledge of the number of receivers. The multicast uses network infrastructure efficiently by requiring the source to send a packet only once, as Greg mentioned. If it needs to be delivered to a large number of receivers, well, the network switches in the network take care of replicating that packet to reach multiple receivers, such that streams are sent over each link of the network only once. So let's review what multicast is and when should we use it. Multicast is one-to-many. It does scale very well. It uses the network really efficiently. Network switches handle the details in the distribution, not the sending device. It does use UDP packets, so that means the network has to be perfect, basically. We can't stand any missing packets or malformed packets. We depend on the network delivering each packet accurately. There won't be any resends. And packets must be received timely and orderly at each receiving location. Network switches need to have IGMP, or this awareness of multicast, and the core switch has to have what's called an IGMP querier. When do we use multicast? Well, when we have a local area network, when we want something to act kind of like a distribution amplifier, one to many. When we want to be able to subscribe to a stream and then leave that stream. In other words, not necessarily a permanent connection, but we want to at will dynamically change things. When we want to route media, again, when we want to route that media dynamically. And the receiver gets to choose what channels it's going to listen to. And the sending device isn't even really aware of how many receivers are listening to it, or that somebody has subscribed or unsubscribed. So let's look at Unicast here in the same way. Again, that's a one-to-one transmission from one point in the network to another one, and that is a sender and one receiver, each identified by a network IP address. So what is it? It's 1-to-1 over IP. It may not scale well because there's going to be a bandwidth limitation at the sending end. If 200 receivers, want to get this stream, and we try to send 200 streams, well, that's 200 times the bandwidth of each individual stream. So it can add up to a lot pretty quickly. It's a separate end-to-end stream for each and every destination. It does use what you might call unsophisticated switches. So that's a benefit. It doesn't have to be UDP packets with Unicast. This can be TCP, although typically in an AoIP network, to minimize latency, we're going to use UDP packets. So therefore, we do expect, again, a perfect network here since we're sending UDP. UDP easily transfers routers with port configuration, and I should say UDP and in Unicast. So Unicast can easily traverse a router just by doing port forwarding configuration. So it is okay for remote operations through things that that can't accept multicast. They can certainly do Unicast. When should we use this? Well, anytime that we have a local area network, that's fine for Unicast. But we can also use Unicast over a wide area network, and we could use Unicast even over the public internet, realizing that if we're using UDP packets, there won't be any resends of missing packets. The sender does continue to send even if the receiver is no longer interested or drops offline, goes away, gets turned off. The sender just keeps on sending what it was originally told to send. So therefore, Unicast is best for definitely fixed connections. Yes, I want this to always send to there. I want it there all the time. That's how we typically will use Unicast. And the receiver cannot choose channels. The receiver can't tell the sender, I'm interested in this audio or that audio, or you can stop sending that now. That's configured in the sending device. So control of these things is with the sender. So what are the implications of using Unicast IP media connections in a data center and a cloud location? Well, Greg tees up that question and gives us a fuller understanding of what's involved here.
The question is, what are the practical implications of using Unicast? So I think there's at least two main things to say right off the bat first. First of all, it essentially adds a little bit more management of the connection. That's all. In terms of being able to do everything, yes, you can do everything. I mean, look at what we're doing here today. We're watching a webinar ahead of time. We recorded this webinar, multiple people on the screen. This is all being done with Unicast. This is all being done over the internet. So it's not like it prevents you from doing anything. The second important point to mention is this is all completely still in industry standard. AES 67 contains, in fact, requires vendors to implement the AES 67 Unicast mode. And this was the reason when I was on the committee and we talked about this. Telos has been the company, have been doing long distance codecs with the Zephyr forever. we've been solving this problem of, how you do a remote broadcast. We knew that when the day came and the internet and the IP network speeds would be sufficient to carry uncompressed audio, the megabits of audio, what we were doing inside the facility with Livewire would then be able to go outside the studio, outside the facility, and start to connect in between facilities. And for instance, now with the cloud, this was back in the year 2000, long before AWS or Google had, cloud facilities. But because we've been in the business of doing long distance connections, we knew how important this was to think ahead and put the Unicast mode in AES 67, and that's why it's there. So some of the friction is just because it's different, and you don't decide on channels, Livewire channels. You start addressing things specifically with Unicast addresses. But again, like I stressed at first, it does not take away from being able to get the job done.
Now, since multicast audio streams have been so highly touted in AoIP systems, we might ask the question, was there any audio penalty for using Unicast IP streams? Here's Jake.
There is no difference when we talk about the actual audio quality between a multicast or a unicast stream. We're merely talking about the transport method, whether it's a multicast channel that devices can subscribe to or a unicast stream that is sent from one point to another point directly. That's the only difference between the two. The audio quality is exactly the same between those two outputs.
Multicast IP distribution is absolutely commonplace in AoIP systems. But as we move our infrastructure into these data centers or cloud-based environments, we've got to rethink multicast distribution. Now, history is important here, as is a working knowledge of multicast distribution. About using multicast IP, which is what we've always used for audio over IP in an on-premise situation. What happens when we move some of our equipment into containerized software in a data center? Maybe we have control of the data center, maybe we're renting space there, or into a cloud environment. I guess what I'm asking is, where does multicast, that protocol, that addressing scheme, where does that start to not be desirable in audio over IP? Greg?
Back in the early 2000s, in the dot-com heyday, they actually tried to make the internet carry multicast. This was kind of the big plan. It was called M-Bone, M-B-O-N-E. Instead of, backbone, it was the multicast backbone. And one of the things that shot it down was the fact that, remember, we were talking about multicast as kind of channel-oriented. People had to share and coordinate who was using which channel. And that turned out to be much more difficult, to administer and to get people to cooperate and come up with a master plan, because, one of the basic things about the internet is it's unplanned and it just works, because that's the way it was designed back in the 1970s. So the ability to make a connection independent of what everybody else is doing is really the strength of what the internet's all about. So this question really comes down to taking advantage of that property of the internet, which means you can make a connection and put some data through independently of what everybody else on the whole planet is doing. That's what the internet does best. If you're connecting to that data center, if you have a private network, you can go ahead and use multicast because you're in charge of it. But if you're connecting over your ISP or the internet, you then have to, go by the point-to-point connections, which is Unicast. So, as we've talked before, it changes the way that you have to approach handling and managing your audio content. And so that's the point where you want to take advantage of an available facility, whether it's what's called a private cloud, which are companies that they specialize in. They're going to host the rack rooms. They have the real estate, all the way to the public cloud, which are, the AWS and Google and Azure's, where they already have these massive facilities, and you just have to pay the money, to take advantage of it. Because of the connectivity, then you have to change the way that you work in terms of your audio connections.
Jake, Greg's just talked about multicast over the public internet and then getting into a data center. What about when we're in the data center? I'm given to understand that multicast is not always a solution in a data center, but we need to use a different addressing scheme called Unicast. Jake, can you talk to us about that a bit?
Sure. So Unicast is a one-to-one peer-to-peer connectivity method. It's similar in some ways to multicast in that it is an address-based system. It uses, we can send audio, but it's one-to-one. That's the key difference. That's the uni in Unicast, right? And so when we look at building facilities inside of a data center, whether that be a private data center that you might build out and own, or whether that be a public option like an AWS or an Azure, and then there's sort of a gambit of discussion inside there that's the middle of that spectrum of options. There are reasons that you may or may not need to use Unicast. The big reason we jump to using that point-to-point connectivity of Unicast is when we need to send things over networks that lack that multicast manager. And if we sound like this conversation here today is a little bit familiar to you, it's because it's the same question we've been talking about for 5 or 6 years now, at least when we talk about multicast and AES 67, because part of the benefit of AES 67 of what it brought to the table was a standard for unicast interoperability modes. So that does exist. So that's, a very strong and well-defined industry standard that is available for tooling, and it has certain use cases. But to Greg's point, you can't do that jump in and monitor moment like you can with multicast, where if I have a multicast source, I can have an X selector in a physical plant deployed somewhere and grab the same stream that is feeding an X node that's also feeding my STL. And in the cloud, there are ways we have tools that you can jump in and listen to that stream or monitor that stream and see if the packets are all right and the timing is correct. And those types of tools exist. But you can't do that with Unicast between the devices. You can't jump in and get that sort of virtual bud set type experience with Unicast. So that's the downside. But the primary use case is joining places where we don't have that multicast management layer available to us. And there are a variety of places where they're also either due to cost, we might not want to use multicast, or there are some premium offerings where you may be able to purchase multicast in a cloud environment or a data center.
Well, now's a good time for us to mention you can please feel welcome to ask your questions as we go along. There's a Q&A button on your webinar interface. Some questions we can answer privately. Others we'll answer at the end of this webinar. So feel free to use that. We've got experts standing by. When familiar processes take on new forms, sometimes it takes a couple of rounds of explanation to completely grasp the new ideas. I know it does for me, as Greg and Jake can attest to. I've talked to them many times about these concepts. Here, I'm having both Greg and Jake explain how software containers can and indeed do share audio between and among themselves. So it sounds like when we deploy software containers in an on-premise situation, like in my radio station, in my broadcast facility, if we deploy that on-premise as part of maybe an already existing or a new LiveWire or AES 67 network, there's really no difference with connecting those computers with software containers as to connecting appliances that have LiveWire or AES 67 IO. They're going to connect, go back to a switch, and we can treat them as inputs and outputs on the network. Am I thinking about that right, gentlemen, or am I? Is there anything I should know extra about that?
No, that's exactly right, Kirk. And it brings to mind what I used to say before we had our products as containers and software. What is the most valuable thing that audio over IP connects to? And the answer to that question is software. It opens the door to pure software. It opens the door to what we're doing today. A lot of our products, a lot of the Axia products have been essentially a software product delivered to you in physical form, but this is how it worked. So As Derek Pilkington, the vice president of engineering, often likes to say, what we're doing now is we're getting that software product out of that box that you've always had. That is how Axia has always worked, and just delivering to you the software piece. So it works in exactly the same way. And this should be a comfort factor for anyone who's familiar with Axia and Livewire, that it is no different. It really is absolutely no different.
As we've sort of talked about, and Greg hits it perfectly there. I mean, we're taking the software that's been in the box for decades and taking it out of the box and giving it to you as pure software. So you can bring the box to the table and use a server that you're able to source. And there's a whole bunch of financial and business reasons we've covered in other webinars in the past that talk about why buying computers is more beneficial than buying an appliance. But you're still able to work in a very similar way when you vend the software only solution. And that familiarity in the on-premise environment, we worked very, very hard when we were thinking about and planning this move to deploy software options to make sure we only introduce degrees of newness where degrees of newness are necessary. And one of them is not necessarily in the AoIP transport mechanism inside of a facility. Multicast audio works really well. Livewire is a mature and stable protocol. There's no good reason to move from what is stable to what would be new or unstable without good cause. So in an on-premise system, that's the reason we stay in the multicast world 9 times out of 10.
So today's hard drives and local area networks, they have enormous capacity for audio data storage and transfer and distribution. We don't need to reduce audio files and live audio. We get to handle audio completely in its best form, which is linear audio. Now, this is true as long as we keep our audio within the LAN. There are still good applications for audio codecs, however, when long-distance infrastructure, like the public internet, isn't adequate for live linear audio. Greg Shea discusses those times when linear audio actually isn't the best choice.
First of all, you need the ability to handle the higher bit rates. So for a stereo stream, it's typically around 3 megabits. Now, that used to be a big deal, 20 years ago. Getting 20 megabits for a WAN connection, for instance, was basically impossible or, exorbitantly expensive. And getting the bit rate down is one of the main jobs of a codec, just because of the economy of, what is affordable for the bit rate for a long distance connection. But there's another second point, which is equally as important. When you go over a long distance connection, often the data is not as secure or as perfectly transmitted. There are bit errors, dropped packets. Perhaps there are timing jitter and some packets arrive out of order. These are all things that just happen. You can't do anything about them in long distance networks. It's not perfect. So codecs have the ability to use algorithms, whether it's error concealment or using error correction codes, whereby what you do is you compute what maybe the missing bits were by sending some additional information. A very simple way is you can have two copies of information, but error correction coding is all about getting the benefit of being able to correct for missing information without sending a whole second set of the data, which of course, costs more for the bandwidth again. So those are the situations, whether you have a not clean enough error-free connection, or you don't have enough bitrate to carry it uncompressed. On the flip side, if you do have, for instance, on a local area network, the cost of the additional data capacity, in other words, having nowadays a gigabit connection or even 10 gigabit in your back end of your switches for your trunks, that can often be less expensive. The bandwidth is less expensive than having to use the compute power, buying the MIPS or buying the codec when it used to be a physical device to use a codec there. This was part of the origin of why Livewire was uncompressed in the first place. because the bandwidth was cheaper than the codec. But you may not always have that choice. If you're going over the internet, typically is when you can't pay more to get a perfect internet. Some people wish you could.
So what networking scenarios trigger the need for audio codecs? Well, Jake walks us through that decision process.
Any network where you can't guarantee you're going to have packet perfect transmission is a place to consider the use of a codec. Now, some of us who sit and, talk about the nuances of networking know there is no such thing as a perfect network. But by and large, if you're building an AoIP facility today, we're buying discrete switches, we're buying discrete hardware, whether that hardware is hardware to run software with containers on it or discrete appliances. We're buying all of these devices and creating a very controlled environment where we can almost guarantee perfect transmission. When we start wanting to send audio over disparate links, we end up talking about needing things like error concealment, which protocols like Livewire and AES67 don't have built into them because we make a trade to have latency. We want really low latency in things like Livewire and AES67 because the mic to headphone latency is really critical to our talent. When we start going beyond the LAN to have either a hybrid deployment of a system where you end up with some resources on the ground and some resources in another facility, or you end up in a facility that is completely based in the cloud and you're sharing resources amongst multiple things in that type of environment, we need to start to consider the use of codecs just like we would for a studio to transmitter link that goes over the public internet or a link to a talent's home because they're working from home right now. That's where codecs really shine. And so there's a place for each tool, whether it's Unicast, Multicast, codecs. It's just what's the connection we're actually trying to make. And that drives what the right tool to use in that instance is.
So how do audio codecs play a role here? Well, to be clear, we're not talking about audio files like MP3 files. We're talking about audio codecs for live audio transmission, what we call a transmission IP codec. They give us reduced bit rate for easier traversal of the public internet at affordable bandwidths. They give us basic error concealment or actual error correction when packets are lost. They can also connect systems with different clock references. So if you've got two different facilities, chances are you have two different clock references, unless you're using a master or grandmaster style clock that is the GPS disciplined. And they also can do sample rate conversion. And sometimes you need to sample, between two of the same rates just to make sure that the clocks match up well. So that's all the things that codecs can do for us. Engineers and programmers alike do get concerned about cascading coding algorithms when audio is sent over several coded audio links and it gets encoded and decoded several times. It's a valid concern. However, using absolutely modern contemporary codecs such as AAC or Opus, and using them at reasonably high bit rates poses very little problem. Linear audio is always the best, but Jake describes the best practice for using coded audio links.
Well, we need to realize that when we start layering codecs the way you described, Kirk, where we have a phone call coming into a facility and then the phone call gets moved to the cloud, and then from the cloud it's going to get moved back to the ground. So when it goes up and down like that, we have a codec in the middle between the facility and the cloud and the ground again. You are layering these things on top of each other, and they have no awareness of the codec that previously was already layered on the audio. So if we can minimize the number of those hops, it's better. If you have to have those codecs, which in many cases we don't have a choice as engineers, we need the compression because the link won't support anything else. Keeping the least aggressive codec settings possible is the most beneficial. So I wouldn't choose a 32 kilobit Opus stream as an example as my to and from the cloud, because it's going to be a very compressed link. I would try and keep that bandwidth as high as possible and really make it a priority to use the best quality codec I could to achieve the minimal number of duplicated artifacts.
So let's dig one level deeper on this topic of coded audio. Greg Shea provides these reassurances as well as some explanation of codec features that either cover or correct for occasional lost packets in transmission.
Modern codecs like AAC and Opus at bit rates around 256 kilobits, even coming down to 128 kilobits, are pretty transparent, are pretty close to your original source material. There's no reason really to run those codecs. You could run, typically the maximums are maybe 384 kilobits. You could run it there if you want. And that's still almost a factor of 10. Remember I said uncompressed, it's typically around 3 megabits. So you get the data reduction benefit, and in the configuration of the codec, you typically can have choices of whether you're asking it to do the extra work of the forward error correction. And so if that's your intent, if the whole reason you're using the codec is to get the benefit of that feature, well, then you have to remember to turn it on. So it's not just about the data rate reduction, but you're taking advantage of the error concealment and the error correction abilities of the codec.
So here's a technical review of the cost factors and the technical aspects of these different types of transmission or addressing methods. We have a multicast, which is efficient, it's convenient, it's great for a LAN, easy routing, not supported by the internet, limited support in most data centers, and if they do have it, typically it'll cost more, and it does need a perfect network. Unicast, well, it's less efficient in a one-to-many situation. A one-to-one situation, it's exactly the same as multicast. It's good for a LAN. It's okay for use over a WAN. It's okay for the internet, but it's necessary within data centers that don't support multicast. Usually it's linear audio, so there's lots of data per channel, and there can be ingress and egress costs, or there will be with data centers, especially public cloud centers. So there's a higher cost because this is typically going to be linear audio. Now, transmission codec, well, you don't need that if you're inside a LAN or inside a data center. It is the best choice, though, if you're going across the internet, or maybe if you're going across a WAN, especially maybe a software-defined WAN. That's depending on internet. It has a lower data rate, and so that can certainly save you dollars, perhaps 90% dollars, on ingress and egress to and from a cloud situation. You will have additional delay, so transmission codecs are not good if a talent is listening to himself and then hearing himself back through a codec channel in his headphones. That's not good. You've got to provide some different kind of audio routing there. Codecs, though, and this is a key one, can provide error concealment. This is part of AAC and part of Opus. With a minimal number of packet losses, they can conceal that packet loss to where it's either not noticeable at all or just barely noticeable. Whereas with multicast and unicast, with linear data, linear audio, you don't have error concealment there. So some packet loss along the way is actually okay if you're using a modern codec. So while discussing the need for audio codecs in some cases, we've not yet addressed what this looks like in terms of codec deployment. How do you actually put codecs in your data center? Greg explains.
We're living in this modern future place where we're running all of our facilities as server software, and now all of a sudden we're talking about codecs. Well, where are you going to stick the Zephyr, right? We're not talking necessarily about a physical box. We're talking about the action that the codec process takes. We've talked about the data reduction and the concealment of errors. That is available as a software product. It's basically another container. So as you're planning the use of you're planning the setup of your facility, if you have software products on premises running on your servers and you have to get that information somewhere else, the situation that we've talked about that you need a codec, it just means running an additional software container product, of which we have some at the Telos Alliance as products. So we're not talking about a physical box. It's basically another process that you have to add into your workflow.
So Well, we're at the point here where we can review what we have learned over the past 45 minutes or so. Software containers send and receive audio over IP just like hardware boxes do. There's no difference there. Containerized broadcast infrastructure easily shares audio with networked hardware devices. So your software containers can talk to your hardware devices over that same AoIP network. Now, within an AoIP LAN, we can continue to use multicast AoIP, just as we do with all networked hardware devices on a LAN. Containerized software operating in data centers is likely going to need to use unicast audio over IP, as most data centers don't support multicast, at least not yet. And AoIP is the same linear audio as multicast AoIP, but each stream destination has to be specified in the configuration of the sender. And when our IP transmission path may lose occasional packets, we need to use a transmission IP codec. So modern codecs have error concealment to minimize or eliminate audible artifacts caused by packet loss. And that packet loss is specified typically anywhere from, it can be up to 5% or 10%, as long as it's statistically distributed. Yeah, if you lose, 300 packets all in a row, there's going to be an audio problem. But a packet here, packet there, packet here, packet there is easily covered by these codecs. Using multicast, unicast, or IP codecs where appropriate allows us to build largely virtualized broadcast infrastructure. And systems can be hosted on premises, in a private data center, or public cloud space, or a mixture of these, whatever is appropriate for your workflow needs and your business needs. So what is coming up next at Container University? Well, we have 3 more Container University webinars. Container University 203 will be a decision process here, on-prem, data center, or cloud. Where is your virtualized broadcast neighborhood, or where should you move? Container University 204, staying in sync without losing time. We talk about clocking of these different systems. And Container University 205, security versus convenience. Smart network planning can allow for both a secure environment that is not inconvenient to use. I hope you've enjoyed this, and I'll ask either Lindsay or Angie, whoever's going to come on and talk to us about if there's any further Q&A that we need to discuss.
Thanks, Kirk. We do have a couple open questions in the box that we will get back to those people. When you registered, we received your email, so we will go ahead and get those to you via email, because I have a feeling this is the end of the webinar and Lindsay's ready to close it. And as soon as we close it, we won't be able to post those answers. So Cam, I will maybe throw it to you in case there's any of these that you want to answer publicly. Otherwise, we can toss it back to Lindsay to close us out.
Thanks, Angie. I don't think there's anything in here. We've got some great questions. You kept our keyboards busy this time around, so we appreciate all the engagement here. We're definitely trying to get all these questions answered, so we will throw these, as Angie said, in emails. And if you have other questions down the road, or if you're watching this webinar offline in a recorded session in a few days or something like that, always reach out to our team, and we're happy to take care of answers and continue the education and make sure that you guys are armed with all the right information as you move forward on your journey into containers.
For sure.
Great.
Well, thank you, Kirk. Thank you, Angie. Thanks to the whole Q&A team. I know you folks were busy bees answering all those questions and then some. So thank you again for attending this webinar. It will be available to view by the end of the week, and I will send a recording to all of you via email. And then last but not least, if you would kindly take just a few more moments of your day and share with us the feedback. There's a survey that will pop up on your screen once I close this webinar. So if you would just take a few moments and give us some of that valuable feedback so we can better serve you now and in the future. So for now, see you in a couple weeks, and have a great rest of your week. Thank you.
Thanks, everybody.
Thank you, everybody.
Thanks, guys.
Bye.
Bye-bye. See you.